Okay, today we're talking about data and sampling. Now what's really interesting about having discussed creating averages and standard deviations and what they mean, now it's time to talk about how we gather the data so that this can happen. And so we begin with a population that we want to study. First off, it needs to be well defined. And this is far more important than most people actually realize, and that is the well-defined nature of your population is crucial so that you don't make small mistakes in creating an interpretation of what's going on. Now, once you have a well-defined population, you want to be able to measure something from the population. So we're going to measure something. Now, measure could be as simple as asking an opinion poll, or we could weigh something, or take a measurement of its length. There's lots of things that we can do. So what happens when we do this, we have to make sure that this sample that we get, that we've taken the time to do this, is representative of the population. So we want our sample to represent the population. As an example, what would you hope for as a representative sample of a population that might be the Augustana students? Well, what characteristics does the population have? Well, we know that there's more women than men, so one would expect a representative sample would also reflect that. We have a stratification of freshmen, sophomores, juniors, seniors, some high schoolers and some post. So it would be interesting if we knew how to be able to get that into our sample. But the problem is, we may be wrong about what we think we know about our population. So we have to be very careful when the population is very, very large. Frequently, we have no a priori, it means in advance, knowledge about the population. So therefore, constructing a sample is probably out. We don't want to construct it in such a way to guarantee we have enough women and men, and enough sophomores and freshmen, etc. So we have to be very careful of how we construct our choices for creating a sample. All right, so let's just go through some sampling techniques, and we'll point out some of the difficulties that they represent. So first we're going to begin with a very simple sample, and it's called a volunteer. A voluntary sample. So you go to a restaurant, there's cards out there and you want to evaluate your server. Or you walk by a store and they have a chance for you to express your opinion. And so you choose to participate. Now, the problem with voluntary samples is that there's often a motivation towards the positive and the negative. There is a double bell-shaped curve that's happening, as we call extremes. The really like to really hate. In other words, it's very possible that the people that have an ambivalent opinion, oh, service was okay, don't have a motivation to grab the card and give their evaluation. So voluntary samples already seem to create a description of a population that's bimodal, when in reality the population may not be bimodal. There may be lots of people that, slightly apathetic, didn't take the time to fill it out. So we don't like voluntary samples because of this process of extremes coming into play. And in general, mathematicians fear voluntary samples. So we try to stay away from them. Next one is considered a convenience sample. For example, I could ask all of you in the class to email me your opinion on Augie's tuition structure, or email your opinion on Augie's intramural programs. Well, you're a sample that's convenient to me. I have all of your email addresses at hand. I probably can get a reasonable number of you to answer right away. So, in a sense, the convenient sample gathers data very quickly. So the advantage of the convenient sample, it's quick. But because it's quick, it usually is biased. Now, the mathematical word for biased means that it can shift in one direction or another. It doesn't have to be like the voluntary, which often has two biases. They shift to the extremes. It's often biased in a way that there are too many subpopulations are overrepresented. For example, within this class in Math 140, there are too many freshmen and sophomores to be a representative sample of the Augie students in general. Why is Math is a 140 level. There's not that many upperclassmen as compared to freshmen and sophomore that come into this class. Because it's quick, it's also cheap. So it looks like if you're looking at samples here, that quick and cheap isn't necessarily going to give you a sample. It's biased in the sense that it's been moved in a direction where the data may shift what's going on. So if these two samples have trouble, one has these extremes in it and causes the population maybe to look two-headed, well, this one seems to be giving too much representation to a subpopulation. What might make a good sample? So these are the bad samples. Now, any sample can actually be converted to a voluntary sample. So this convenience sample could become voluntary if too few people actually answered the question. Let's suppose I send out to Math 140 students. Let's do all Math 140 students. I think there's 3 sections. So let's send out 90 emails, but only 30 people respond. That would be like a 33% response rate. Well, what that's done is, even though we've asked lots of people, only the people that really chose in such few numbers to volunteer to answer caused the convenience sample to become a voluntary sample. But let's say I asked you guys and every one of you responded except for one, so I've got 99.9%. Well, then the convenience sample was not converted to a voluntary sample. So we have to be careful of what we call conversion to voluntary. And so we're going to look at response rates when we ask people about their data collection, how high was their response rate. And we're going to come up with some standards to say, oh, you got too few of people as a percentage responding. Your data, your sampling technique is being damaged by this voluntary double bias. Now, let's construct a couple of good samples. So let's pretend I know absolutely nothing about Augie students. So let's just consider the population of Augie students. And I go to the registrar, and the registrar has a list of 2,100 active Augie students. And I just pull names out of a hat. So I randomly select Now, the beauty of random selection is that if I randomly select enough, I expect to get about a quarter freshmen, about a quarter sophomores, about a quarter juniors, about a quarter seniors, some high schoolers but very few, some super seniors, etc. In other words, the random selection, when enough is made, should start representing the distribution of ages at Augie. Suppose you take a single dice and you shake it. You shake it one time. Let's say you got a 3. Well, Is that 3 representative of the dice? Probably not. Could be almost anything. Let's take it 20 times. And let's suppose we have 4 1s, 3 2, still just 1 3, 8 4s, 2 5s, and 2 6s. Now, this could happen. Maybe you had a string of 4s and some 1s or whatever. We don't really know if this is bad, but we do know that there's a heavy variation in that sample with a die that we wouldn't expect so very few 3s and so many 4s, but it was done randomly. But if you had shaken a die, say, 20,000 times, you know what it probably looks like? Probably looks like this. It's all very, very close to 1/6 of the time. It's not exactly accurate, but with enough samples, it's simply almost a flat line. In other words, the randomness starts doing something when you do it enough that it becomes predictable. So when I randomly select Augie students, if I select enough of them, I can predict that I expect it to have a representative percentage of freshmen, a representative percentage of female students, a representative percentage of athletes, representative percentage of bio majors. In other words, since I'm picking it randomly and I'm not imparting any of my opinion into this selection, if this is large enough, then we are confident our sample is good. And good usually attributes to the term unbiased. And the bias, again, mathematically means that we haven't shifted an opinion or a measurement in a specific direction or directions. As an example, if we had gotten too many non-athletes in a survey about intramurals, maybe we would get too many people saying that it's not enough. Well, it's very likely that the athletes are not as active in the intramurals and might be very happy with what they see, so they say it's enough. It's very easy for a bias to be created because the sample doesn't represent the population. When we randomly select participants, we become confident that our sample is good. Now, random selection is difficult. Now, not to mean to pick on some of our students that go to Augie, but we have several Chinese students at Augie. Now, the population of China is very large. How can I reach into the population of China and randomly select some people? So, random samples have some characteristics that make them difficult to be done. It's actually hard to do with large populations. In fact, you could write a book on how we should be able to find out the opinions of American teenage men. Lots of men out there, a lot of teenagers. How do you make sure you get a representative sample? Are you going to get people from Arizona? Are you going to get people from Alaska? Are you going to get athletes? Are you going to get atheists? Are you going to get Catholics? It's hard to do, really hard to do. The second thing is it's difficult inherently to be random. So how do we select things randomly? I can't put 400 million people's name in a hat and draw them out. If I start using a computer, computers have a little bit of determinism. They're very hard for them to generate things randomly. It's actually, for a long time, been a question about mathematicians and statisticians. How do we guarantee our method is truly random, that there's not some bias in the method in which we're selecting? In addition, it's difficult to have a high response rate. How do we get people to participate after we've selected them? I mean, my famous example about the difficulty of how participation affects things is that we've had several presidential elections where things did not turn out as how the statisticians and pollsters thought they were going to. Why? Well, one of the problems could have been people simply saying, bug off, I don't want to answer. That they used data with too low of a response rate, and so we didn't get good representative samples. So we'll address how to improve response rates, but we need to be very careful in addressing how the sampling method was done. Wow, so it's hard to be random. It's hard to do with a large population. It's difficult to get the response rate. Man, it seems like there's lots of problems with it. Well, it even gets worse. It's expensive. Because we want enough people within the random sample to make sure that we are representing the population. So to reach out there and get it done professionally or properly is very important, and because expense is included, it becomes difficult. This is by far the best. Now, in order to be random, we like the sampling to be what we call simple random samples. So we're going to put an S in front of it, and that means that the randomness was basically done by shaking a die. We took a die and shook it. Now, they have 100-sided dies, etc. So in your book, you're going to find out that we have tables of random digits. What do these tables of random digits look like? Well, they're just simply numbered rows with numbers that go across them. And these numbers that go across them were literally one of 10 digits, 0 up to 9, that somebody shook on a 10-sided die and wrote them down. We had thousands of Army, Navy, and Air Force people shake dice, record their answers to create these random digits. Why? Because it's difficult to be random. Now, when you have a random table, it's very easy to use it, but you have to be careful that you aren't being silly. Let's take, for example, our students. Let's say we have student A, student B, all the way up to student Z. That's 26 students, right? How do I make them into numbers? Well, the easiest way is to use a list of numbers that will be uniquely attributed to them and be as small of a list as possible. So I could do 1, 2, all the way up to 26, but it appears that this number is a different type of number than that one because it only uses one digit. So our standard thing we do is to make them all uniform is everyone has the same number of digits. So now I've assigned people the numbers from 0, 1 to 26. Or I could have done something like this. A is 31, B is 32, C is 33, etc. and gotten a different list, just some assignment. So this is called the assignment. You just make it happen. Now, a bad assignment would be used too large of a number. Suppose we have, again, A up to Z, and I assign this guy 9,972, and the next guy 9,973, onward. Well, now the digits are so long, they are going to affect how we get them, because what we do is we read a random number table, we read these, and we read the number of digits that are in our assignment, and we see if the number of digits hits our assignment. If I used 4 digits, what's the chances of me reading the first 4 numbers and seeing in that list? There's 10,000 some numbers that are 4 long, and I'm only trying to hit one of 26 of them. That makes my life harder. So don't use too many. Now, let's use a reasonable one. A is 0, 1, B is 0, 2, up to Z is 26. How do we use this table? Well, usually we just simply open the book and we pick a row. Once that's fixed, now we read it in a very specific way. Since I have 2 digits, I read the first 2 digits and say 76. Do I see it in my list? Nope. Cross it out. 38. Do I see it in my list? Nope. Cross it out. Now, these tables often have spaces, so now comes 52. Is it in my list? Nope. Cross it out. I'm being unsuccessful. Is that a surprise? Well, 26 numbers out of 100, I kind of feel like I got about a 25% chance of actually hitting one on a random. Well, I missed 3 times, but look at, here comes 10. So I just picked the 10th person right there. Continue. Now, we're not allowed to reuse the 10 that we've already picked, so the next 2 numbers get crossed out. Then comes an 87, then comes a 55, then comes a 30-something here. This is how we reuse the table. And we get to the net end, we take that number, and we continue in the next table, skipping nothing except for the spaces, reusing no numbers, reusing no selection. We're always we're not allowed to ask one person or measure them twice. This is how a random number table is used and how we can assign it to people. Now, all of you at Augie have an Augie ID. I think most of your IDs are 6 digits long. That covers 1 million numbers. And there's only 2,000 students, so if I use your Augie ID, I got a 2 out of 1,000, a 1 under 500 chance of reading the number table and hitting one of your IDs. I'd have to read a long time in that table to select a large group of students. So it's very likely I wouldn't use your Augie IDs. But I might use those numbers to create smaller numbers. Like, let's suppose I take all the Augie IDs and I find the smallest and subtract that from everybody. And maybe that gives me all 4-digit numbers are shorter, and I put zeros in front. Now I got a better chance of selecting them. This is how a random digit table is used, and it's great at selecting things. I will ask you to use a random digit table. Now, let's talk about what happens when we finally get a sample. First off, there's always the question of what can make things bad. What can ruin things? Because it's usually easy to spot things that are wrong. People buy houses and you walk up and it doesn't have a door. Yeah, that's pretty obvious. But the plumbing inside the walls might be a more subtle thing. So let's shoot for the obvious things that can ruin our work. Well, the first is non-random. If it's non-random, I'm probably not very interested in it as a mathematician. Second, we've talked about how poor response rates convert samples to voluntary. So I want low response rates. They're bad. Non-random, low response rate. Next, is it possible that we have under coverage or over coverage? How can this happen? Well, let's do a little discussion on the most recent census that was done. The census goes out there and counts people. Why do we count people? Well, it's required by our Constitution. Why? Well, it tells us what kind of society we have. For example, it's very likely that in small towns, South Dakota, there are few homeless. So maybe those small towns don't need very much aid in support of homeless. But you go to a large city, let's say Sioux Falls or Omaha, there's probably homeless people there, and we want to count them. But homeless people usually don't have an address, so how do we get a sample of them? How do we guarantee to get out there and talk and count to them? So here's something that can happen really easy. Under coverage by the method of randomness, or the ability to get them to participate, and over coverage because some people really like to participate and get involved. So these can really be damaging to even well-conceived and well-done sample techniques. So, how do we make sure that we can understand the data that we've drawn up? Well, first and foremost is when you gather data, somebody needs to do a complete and thorough write-up on your methodology. Methodology. In other words, when you gather real data, you explain what you did, how you did it, who did it, the methods that were used, the questions that were asked. This is crucial. This is often referred to as metadata, things outside of the numeric measurements themselves, but this is how we can determine if you inadvertently were non-random, if you inadvertently had low response rate, if you inadvertently had under coverage, and whether or not I should trust your work. The second thing is the data needs to be made available, so other people can look at it, make sure that you've done things correctly, even down to how questions were asked. Now, let's talk about how questions were asked can ruin things. Obama's election showed that it was very difficult to ask human beings a human question. At one time, they predicted that he would receive almost 80% of certain areas voting. Why? Well, it turned out there was solidarity in how people responded. In other words, if you were a black man being asked if you're going to vote for Obama, they felt compelled to say they were going to, even though they might not want to. In other words, asking of the question that is personal leads to a difficult conundrum. How do we know the people are going to be honest? Is there peer pressure to answer in one way or another? If you read about the history of Masters and Johnson, you'll discover that personal questions with regards to human sexuality was a very difficult thing to do, to study and find out what is happening in society. In fact, society is always asked a question about sexuality and am I normal? What do other people do? How many people do people date? It's a very difficult thing to talk about, and it's extremely private. So I can imagine very easily if you went to the college dorms and wanted to ask people about their sexuality, how low a response rate it could be. And if you had a high response rate, now comes the strange deal with the form of the questions. It's called connotation and clarity. Connotation is when you use a word that has a meaning that may move a person in one direction or another. As an example, just recently the Argus Leader had a headline saying that Kristi Noem cashed in on the COVID virus. Now, the very term cashed in, it refers to somebody going in and getting cash out. Now, we know she's not getting cash in that way, but what is she doing? Is she gaining political clout by being a libertarian type government saying that we're not going to apply restrictions in South Dakota because that's who we are? Is that how she was cashing in? Or was it that she was raising funding for her political campaign? The words that were used had an implication, but might not have been exactly what the story was about. That's a connotative use as a word. If you want to ask somebody a personal question, you need to use bland, simplistic questions. You need to not load it with words that can be viewed as being pushed in one direction or another. You also have to be kind of repetitive. Ask simple questions where they get involved so that when the harder questions comes, they actually answer. Clarity is important because you don't ask negative questions. Aren't you going to the movie? If someone says yes, is that the same as are you going to the movie? And it says yes. It varies by language. You ask a negative question in Japanese, then it is answered in the negative when it's an affirmative in the affirmative. It means that answers change. But most Americans don't answer negative questions. In fact, aren't you going to the movie is, no, I'm not going to the movie. We have an answer, but then we clarify it. So it's very important that we have clarity in our questions. So the design of questions to measure people's opinions or get data is extremely hard to refrain from any connotation and to achieve clarity, non-ambiguous. You also never ask complicated questions. Any lawyer will tell you that when they're working on a case to before a jury, that they need to suppress the complicated arguments and use simplistic ones that maybe have to be put together, but really delve into a simplistic piece of information, go to the next, simplistic, so that people can synthesize it all together. It is very hard in short, little questions to get complex issues brought across. And so, as soon as you come into the human mind, if you're not taking out a tape measure and measuring it, complexity causes some issues. And complexity also brings about the subtleties of a language. Where did you put a comma? Was there a bad pronoun in there? You guys took your freshman course on these pronouns that could be unclear, right? So you don't know who they're referencing. This can cause great issues. You all heard the T-shirt joke that says, save lives, learn grammar. And then on the back of the T-shirt says, let's eat grandma. And there was no comma between let's eat and grandma. Are you going to eat grandma, or are you asking grandma to join you for dinner? It's really important that these small things are observed. Now, that's the first part of sampling. The next part is going to be not just gathering data, but gathering data where we want to understand what may have happened, that we're manipulating things. And these are called experiments. So our next thing we're going to talk about is experiments. And that's a little bit different because prior to this, we're just trying to measure things. And measurement could be an opinion, measurement could be a height, but in no way are we interested in the effect of a drug or how the advertising did on people. We're just asking or gathering data. That's very different than an experiment. So what should we call what we just discussed? Those issues all deal with observation in general. And we are going to talk about the same issues with regards to experimental work. However, experimental work is going to require some extra steps. I think everything that we've talked about for the observational side, to measure and look at things, is going to be required to make good experimental data.